Okay, would you please join me in welcoming Mr. Tom Luster.
I'm Tom Luster. I'm with the California Coastal Commission. I review desal projects up and down the coast, and I'm going to tell you a little bit about desal tonight. It would take many, many evenings like this to talk about all the issues involved, but we can get started anyway. Let's see, maybe it would help if I load the program. Thank you. There we go. Okay. Let's get started. So I've been asked this very simple question: can desal solve the state's water problems? I'm going to start with the answer right off the bat. The actual answer is it depends. I mean, how much do you want to spend? What sort of environmental damage do you want to have happen? How much are you willing to put up with? How much plumbing do you want to add? All those questions go into choosing desal, not just statewide, but for any particular locality that might be interested in desal. I'm going to cover just a few of the many issues, and hopefully leave plenty of time for questions and answers if you want to dig into some of these other ones in detail. But I just picked a couple that I'm involved with a lot, and hopefully you'll find them interesting, but we can branch off depending on your interest. I want to talk a little bit about what it is, where it fits into the state's water supply, and a couple of key elements that we look at when we're considering designing and planning for desal facilities, specifically the marine life effects and integrating the state requirements with local interest in water supply. So, water in California. Desal is really no different than any other big water supply in California. It's controversial, contentious, takes a long time to get decisions out. There are lawsuits, all that sort of thing. Desal is no different. It's just moving California's usual set of water issues to the coast, which has its own set of issues because everybody loves the coast. There are beaches, there's marine life, there are very expensive real estate, there's all sorts of pressures on the coast, and so you're bringing all the California water issues to the California coast, and it makes for a very interesting review process and decision-making process for everybody involved. That said, California has been doing desal for a while. A lot of desal, a lot of the basic technology that is still used today in desal was invented in California back in the 60s. Some of the early plants, Santa Barbara had one early on, that Steve mentioned. A lot of the research out of San Diego, the Navy, after World War II, started putting a lot of emphasis on desal research. And so down at Point Loma and the San Diego Naval facilities had a lot of desal research back in the 60s and 70s. There are a number of desal facilities on the coast right now. They've been there for years. They're very small for the most part. Most are used for a single purpose, like a power plant will have its own desal facility because power plants need very clean water in their process, and so they produce their own essentially distilled level water to use in the power plant. The Catalina Island has a small desal facility that provides water for the town. There's one in Sand City near Monterey that's been there for years and provides a little bit of the town's water supply. But these are all a couple million gallons a day or smaller to provide just what's needed in that local area. There's also a lot of state interest in funding desal research. The Department of Water Resources has given away something like $50 million in the last couple of years from Proposition 50 grants for different types of desal research on energy efficiency, on different membrane processes, on seeing if you combine different desal methods, if you'd get a better product or a cheaper product. So the state's been doing that for a while. There were a lot of permitting issues with desalination, and so the state has an interagency work group where if you are proposing a desal facility, you can meet with this group, and it includes representatives from all the permitting agencies and all the various resource agencies to find out what questions they have, to get guidance on how best to go through the process, to see if you need to make any changes in your original idea to make it an easier process to go through. And every 5 years, every water district in the state above a certain size has to look at desal and consider whether it would work in their area or not, if there are opportunities for it, if they want to identify particular projects, desal projects that they expect to rely on sometime during the next 30 years. So they'll project their expected growth, their expected water needs, what projects they have in the pipeline, and determine every 5 years whether desal should be a part of that or not. And the next round of these urban water management plans comes out, they're all due in July this year. So we'll see perhaps a whole new batch of interest in desal at the local level. So all these are going on in California. It's all been, up until the last few years, kind of small scale and quiet, but there are some big projects out there, and with the drought, there's a lot more attention on desal, and can it make a difference in California's water supply? The Coastal Commission has approved about 30 desal-related projects over the last 10 years or so, ranging from the full-scale facilities. Steve mentioned the plant in San Diego, the Carlsbad facility, at 50 million gallons a day. It's the largest in the Western Hemisphere. We have a number of research projects that we've permitted where proponents will go out and figure out not only desal methods, but try to identify the best site to put a desal facility. You'll see in a moment the advantages to using a subsurface intake, and there are only certain locations along the coast where you can site those. And so a lot of the research has gone into offshore seismic surveys or geohydrologic models to see if you can use that intake method to reduce marine life impacts and get a functioning, feasible desal project at that location. This map changes all the time. There's an ever-changing number of projects. They come and go based on finances, on local decisions to go a different direction. A lot of projects are in competition with one another, and some will fall by the wayside. If one gets to a certain point in the process, the others will fade away. But there's roughly a dozen active proposals in the works right now up and down the coast. Most of them are in Central and Southern California, where the water isn't generally. Along the Central Coast, they're separated from the State Water Project, so they don't have other sources to tap into as much as other parts of the state. Southern California, of course, it's a desert. They don't have much water there, and they have a lot of population. Even with that, I've just heard recently of a couple projects being considered along the North Coast. So the drought has really illustrated in some areas that if you're distant from other water supplies, your existing supplies are being damaged or drying up or being reduced for some reason, desal is being considered in places that you might not think it would be considered until recently. Just a little bit about the process. Basically, you have an intake for your source water, seawater in this case. You have pre-treatment to take out as many of the particles as you can because the next step, the membrane system, the membranes are very sensitive and they need very clean water in order to operate well. And so you've got to have a pretty intensive and expensive pre-treatment system for most desal projects, especially with seawater, because you've got marine life in it, you've got all sorts of contaminants and constituents. It's the same process that you use on brackish water, like here in the valley. If you wanted to use this to treat a brackish aquifer, you could use the same system, membranes, pre-treatment, and all that, to create drinking water. After the membrane treatment, there's post-treatment. Basically, the membranes clean the water to such a degree that you can't drink it. It's too clean. You can't put it in pipes. It'll eat away at the pipes unless you put chemicals back into it that will buffer that reaction to the pipes. And so post-treatment's very important. And then you get fresh water one direction, you have brine the other direction. You've got to figure out what to do with the brine. For seawater facilities, some of them discharge directly to the ocean. Some of them discharge into an existing, like a wastewater treatment plant discharge, which is actually beneficial in a lot of cases because the brine is very dense, and a wastewater treatment system uses fresh water. When fresh water hits the ocean, it doesn't mix very well. And if you add brine, you get quicker mixing in the ocean, and the combined discharges have less of an effect than having two separate discharges. So when there's an opportunity to do this combined discharge technique, we like to see projects go that direction. I mentioned the membrane system. There's all sorts of different membranes and different manufacturers with different particular characteristics. Here in California, all the proposals are membrane. In the Middle East, there's a lot of thermal plants. They have lots of oil, it's very cheap, and so instead of using membranes, for years they've used these thermal systems. It basically boils the water. You catch the steam, cool it, and you get your fresh water that way. Here in the California coast, that would be far too expensive just because of the cost of energy. But in the Middle East, that's a common technique to use. Being from the Coastal Commission, I of course focus on Coastal Act policies. I'll get a little wonky here. Some of the regulations, seawater desal along the coast has to be consistent with all the Coastal Act policies that apply. And these are, it's a wide range of issues, marine life, public access to the beach, visual, all sorts of things. And these are the same policies. We don't have policies specifically for desal. These are the same policies that apply to any industrial facility along the coast, offshore oil, coastal power plants. They all have to meet these same policies. So rather than have specific policies that apply to a particular use, the focus is on what are the resources that could be affected and how can a project avoid those effects. So we apply this whole suite of policies to seawater desal just like we do to any other large industrial facility along the coast. One of the big ones and one of the toughest things for some of the desal facilities to deal with is their effects on marine life. I want to dive into in some detail to one particular aspect of that. It's an important aspect. Not only the Coastal Act, but the State Water Code has specific requirements to minimize entrainment to the extent feasible. Entrainment is when you pull into the intake plankton, fish eggs, fish larvae, the smallest little bits of life in the ocean. They happen to be the basis of the food chain. And so most desal facilities, it's not an issue to, they're not drawing in adult fish. There's screens, they have velocity limits so that fish can resist the the pull of the intake. And so most of the marine life effects that we have to address in looking at desal projects is with entrainment of the plankton in the ocean. And that may not seem like a big deal. There's billions and billions of plankton out there. But back in the 70s, the state recognized through both the Water Code and the Coastal Act that this was an important issue. And so we're unlike most other places in the world that don't have entrainment-related policies. Most places focus on the discharge end of things, the brine that's produced at the end of the desal process. We look at that here in California, but we're also looking at the entrainment side of things. So the easiest way to deal with it is to use an intake that doesn't pull in marine life. There are any number of designs, different subsurface intake methods. I'm going to show a few of those in a moment. And they require specific siting requirements, a certain permeability in the overlying sand, and you got to site them so that you aren't affecting inland water sources, that sort of thing. If you can't do that, and you have to use a regular intake in the open water column, we look at different kinds of screens that you can use to reduce entrainment. It doesn't eliminate it entirely, but it, depending on the kind of species that you're trying to keep out of the intake, they can be more or less effective, depending on the kinds of screen that you use. So the two main intake types, subsurface, open water, pros and cons to each. It's a lot cheaper to build an open water intake, or in the case of a lot of proposals, use an intake that's already there. Just a few years ago, the state came out with a policy to retire most of the coastal power plants' use of once-through cooling, which is when the power plants would draw in hundreds of millions of gallons a day to cool the power generating units, and then discharge that water like 20 degrees warmer than what it came in. That process killed billions and billions of plankton. The state decided back in 2010 to start retiring those systems. So of the 17 coastal power plants that we had 10 years ago, almost all of them have switched to a different cooling method or have shut down entirely and have built a brand new, more efficient power plant in its place. But the intakes still exist, and so there's a lot of proposals to use those intakes for desal or other purposes. If subsurface is feasible, then the state requires that you use subsurface. If the site where the desal is needed doesn't allow for subsurface intakes, then we look at open intakes and the different kinds of screening methods. So open intakes, cheaper to construct, especially if it's already there, but over the life of a desal facility, it may be cheaper to use a subsurface intake, because an open intake, you're drawing in all these plankton and all sorts of things in seawater. You've got to pre-treat to remove all that. That's a huge energy cost to run the pre-treatment system. It has a lot of chemical demand. You generate a lot of waste that way. And so over time, the cost of operating an open water intake may be greater than the cost of constructing a subsurface intake up front, which can be pretty expensive. But you save the operating money. The subsurface intake does all the work for you. You're pulling in practically clean water. In some cases, elsewhere in the world, subsurface intakes don't need any pre-treatment. The water is essentially clean enough to go to the membranes. There's one in Japan that's operated for 10 years or so, and looking at the water coming into the plant, you'd think it was distilled or out of your tap, but all it did was go through some sand to get to the desal facility. So just some examples. The simplest one is just a beach well, a vertical well like you've got in your neighborhood probably. Those work where you have seawater intruded under the beach. In a lot of cases, you can place the wells so that they intercept an area where there's a freshwater and seawater mix, and so you have brackish water, which is actually cheaper to treat. The seawater is about 33,000 parts per million of TDS, total dissolved solids. And it's far more expensive to treat desal or seawater than it is even to treat wastewater, which has levels a third to a half of what seawater is. The more water you can get that has that lower TDS level, the cheaper it's going to be to treat. And so if you've got a well that's over a brackish area rather than a full seawater area, that could be another advantage for siting. Another kind of well is a rainy well, which is essentially a vertical well with horizontal collectors that go out. And so you have much more of a capture area from the same size footprint on the surface. And in expensive beachfront real estate, that could be a real benefit for a facility. If you can get much more water from the same footprint, can be a pretty good deal. Again, these take specific subsurface conditions. You've got to have permeable layers above the collectors, between the collectors and the water column. You can't be pulling water from too far inland and affect good inland water sources, that sort of thing. But in the right place, this can be a very effective approach. And they can be built pretty good size. There are million gallon per day plus rainy well collectors elsewhere in the world. So even for a large plant, if you can put several of these up and down the beach, that can be a good route to go. One of the newer techniques is a slant well. Basically, it's a vertical well, but you just drill it at an angle. There are two right now in California, both being used as test wells. They did a lot of studies at each location to determine the subsurface characteristics, did core samples and seismic surveys and all that sort of thing, and built the wells. One is just north of Monterey in the city of Marina. It's been operating off and on for the last year or so. There's another one down in Orange County that was built probably 5 or 6 years ago. They operated that one for several years, shut it down, but now the local water district is starting that back up again, and they plan to make that the basis of their desal proposal. I don't have a slide of this, but one other thing you can do with a slant well is similar to the rainy well. From the single wellhead on the surface, you can have one slant well that goes out under the ocean, or, and both of these proposals on the coast are going to do this if everything works out. They're going to have the single wellhead, but have 3 wells go out different directions out under the seafloor. So you get triple the volume from the same location. And with a slant well, the maximum extent 800 to 1,000 foot well. So you can get out there under the ocean a good ways and collect 3 times the water that you would from a single well and much more than you could get from a vertical well. In this illustration, I don't think I have the exact figure, but the one in Monterey, the well, the bottom of the well is about 225 feet below the ocean floor. And it's still drawing enough water through all that sand and gravel, acting as a natural filter to get, they're getting 2,000 gallons per minute from that well. And that's just at the test levels. So they expect to get more once they build the full-scale deal. Another system that's, I mentioned the very clean water from the one facility that doesn't need a pretreatment system. They're using an infiltration gallery. Basically, you go offshore, scoop a hole in the sand, and you put perforated pipe below it, connect that to the shore, refill with layers of gravel and sand and that sort of thing. And the seawater gets drawn in through the overlying sand layers, through the perforated pipe and drawn to the facility. This is a pretty promising technique. The largest one in the world right now is a 27-acre offshore facility in Japan. We just looked at one to see if they could build it offshore of Orange County, and it's technically feasible, it's environmentally feasible, it's economically a little costly just because of the scale they're looking at. They want to get 50 million gallons a day, and so that one would have to be something like 30 or 40 acres of seafloor. And that's a lot of sand to move and pipe delay and all that sort of thing. But that's still in the running. There are also some other water districts looking at that option up and down the coast. So that's a very promising system. Here's an illustration of the one in Japan, actually, where there's a single pipe. Actually, I do have a pointer. There it is. I'll use my hands. Single pipe running from shore, and then this is wow, magic. A whole series of perforated pipes, about a little over 1,000 feet offshore. They lay the pipe, they put engineered gravel above it, then sand layer, different layers, and then it just slowly draws seawater through those layers. The draw, there was worry when these first were invented. People said, well, wouldn't fish just like stick to the seafloor with all that suction? It's imperceptible. You can't tell. You know, there are fish, there are organisms living in the seafloor right there. Actually, they help keep the sand filter clean with their biological action. So it's when you put one of these in, you have a temporary impact due to construction. You're scooping up a big area of seafloor. But once you return all the sand, you get organisms recolonizing that area and actually helping the system function. So we're hoping that somebody will find a good spot for this and at least do a test case here in California. This has potential to serve a fairly large facility. So if California wants to take desal seriously and have very few environmental impacts, this could be a good way to go. There's this is kind of an experimental system where it's a horizontal tunnel drilled from the shoreline, and then up from the tunnel you have collectors coming out. And you can have a whole series of these collector wells that extend up and in just before the seafloor. So you're still getting all the benefits of the natural sand filter, but you can, as long as you can drill that tunnel and put collectors, you can collect an amazing amount of water. The San Diego County Water Authority is looking into this system for a project that would provide up to 150 million gallons a day, which would be 3 times larger than the largest one in the Western Hemisphere that was just built in San Diego. So they've just done one of the feasibility studies. They've got another one underway. So we may see this technique in a few years. Again, this takes particular subsurface characteristics. One of the ways they build these tunnels is by freezing the soil as they drill it, and you can only do that in certain areas. So again, you've got to pick the right spot for any of these systems. And as I mentioned, if you can't go subsurface, then you screen the open water intake. There are a number of different systems. This one is probably the one that is going to show up mostly in California. It's a wedge wire system, a cylindrical wedge wire system. Basically, you put it over the end of the intake. The water is drawn in at less than half a foot per second, so fish can swim right up to this thing and swim away. You don't have fish sticking to the screens or anything. And the screen is designed so each little slot is a wedge where the outer part of the screen is very narrow and then the inner part's a little wider. So you keep the smallest organisms out. They can bounce off the screen without being harmed. You're not going to prevent entrainment of the smallest species. And you can order these screens in different sizes, 2 millimeter thick, 1 millimeter, half a millimeter. So depending on the kind of species you want to protect, you can custom order the size screen that you use at your location. So I've gone on and on about entrainment. What's the big deal? Like I said, this is the basis of the food web. And given a particular size of a facility and the amount of water it draws in, it can have a fairly significant effect on local and regional marine life. A lot of the studies that illustrate this or showed us what kind of effects these intakes would cause were from the coastal power plants, which were drawing in hundreds of millions of gallons a day and affecting large areas of the coast. So based on those studies, we're able to scale to the volumes that desal facilities are using. Even though right now desal is overall smaller than cooling water use, the extent of the impact is the same. And I'll show that in just a moment. So, plankton. A lot of my life is plankton oriented, as you can tell. It's the basis of the food web. And seawater isn't just water, it's habitat. And so you're drawing in habitat when you're drawing in seawater. It's a difficult issue to illustrate sometimes because it's invisible. If you're removing 10% of the biomass in a forest, you can see it. You cut down every 10th tree or that sort of thing. It's very visible. Offshore, it's a big ocean. You don't see the missing productivity that you're drawing into these intake systems. But these are the kind of organisms that the food web exists on, and if you draw in enough of them, you're going to have a fairly sizable impact. This is just a simple illustration of the process where you're drawing in organisms. The larger fish can swim back out because the velocities are very low. Once they hit a screen, some systems have a traveling screen where they'll grab the fish, put them in a ladder, and out they go, another chute back into the ocean. But all the smaller organisms go through and get killed due to the pressure in the plant, due to the filters, due to the chemicals, all sorts of things like that. And then they either get pulled out and set aside as part of the solid waste that the plant generates and sent to a landfill, or combined with the brine and back out to the ocean. So you still have biologic material in your discharge, it's just dead rather than alive, so it's a very different thing for the food web to deal with. So how do we figure all this out? So bear with me. The blue triangle is all the organisms that can be entrained. And there's who knows how many species. We haven't even counted them all. um, of all of them, there are some that we consider important, usually fish larvae or crab larvae. And so that's a smaller subset, the lighter or the darker blue triangle. And of those, it takes a lot of work to count these. And so we don't count every organism that comes in there, but we select which ones we want to sample. And so if there are key commercial species like halibut or crab, some of the bait species, they get counted. And so we decide which ones need to be sampled, and then a very small subset of all those, it's usually maybe half a dozen species. Those are the surrogates for all the other species. Those represent everybody that gets in train. And for those, we count how many they are, we determine how far they came to get pulled into the intake, and that generates what's called a source water area. So here's an example for two species. Queenfish. This is for a power plant intake that also happens to be a proposed desal intake in Huntington Beach, which is right about here. And so the intake is about a half-mile offshore here. That intake pulls in seawater from all over the place. The currents bring it in from different directions. It's a seasonal change, all that sort of thing. I'll do white croaker. White croakers, they take a certain number of days before they grow to a stage where they're able to swim away from the pull of an intake. And so I don't even know what white croaker is right off the bat. Let's say it's 12 days. And some of the species are, a couple of weeks, some are 40, 50 days. And so you have different source water areas for each of the species. So if a white croaker gets drawn in here, it could have originated 12 days ago all the way here or all the way there. So this doesn't mean that every white croaker in this area gets pulled into the intake. It's actually a very, very small amount. Lots of them are less than 1% of all the white croaker larvae in this area, 1% get pulled into the intake. However, a small percentage of a large area can still be a large area. And so in the case of these two, this is several tens of thousands of acres of area where the croaker or the queenfish larvae are drawn in. That represents a loss of productivity equal to several hundred acres of the ocean. And so, does that make sense? Even though you're drawing from that whole area, 1% of this area is still a pretty good size of the ocean. And so it's as if you're taking all the queenfish production out of 50, 100 acres of ocean. And you do that for each of the species, each of the 6 species, and you get an average source water area. And they're representing all the hundreds and thousands that we didn't measure, but we consider them surrogates for all the others. Another illustration. So this is related to desal. These are all the former coastal power plants that used once-through cooling in the Southern California Bight. And here's the source water area. This is the average source water area for one of them, where you took the source waters for the 6 species that we sampled and counted, averaged them out. Okay, that's the area they cover. Here's all the power plant source water areas. That's pretty much the whole coast. So you're not removing all the plankton from all those areas, but you're removing 1% of this species and 2% of that species and 10% of this one. And at some point, that becomes a pretty significant impact. And then if you also add in all the protected marine areas up and down the coast, these are where we don't allow fishing, or we expect the productivity to be high so that the fish that originate here can provide for other areas. But now we're removing a lot of those, the productivity from the protected areas as well. So basically, that's what drove this whole interest in subsurface intakes. You completely eliminate this concern from the facilities. And let's see, the Carlsbad facility in San Diego County, it's right about here. So we figured that its source water area was a couple hundred acres of offshore water, about 50 acres of estuarine habitat. They have to mitigate by creating between 60 and 70 acres of estuarine habitat in South San Diego Bay, which is a fairly costly project. There's a calculation we use to get to that acreage number. But in order for them to use an open intake, they had to create a lot of estuarine habitat to make up for the losses. And that's going to take them a while to get that system up and running, and they have to make sure it performs to a certain standard, and they have to make sure it performs to that standard for as long as their desal facility is operating. So that's a cost that, if you're using a subsurface intake, you wouldn't have to deal with. One more illustration. How much water are we talking about? So the source water areas were tens, dozens of miles up and down the coast. 50 million gallon a day facility. It's actually drawing in 106 million gallons per day to create 50 million of potable water, and the rest is a brine discharge. Over the course of a year, and this is the Huntington Beach one, this is 9.5 miles long. That's the entire coastline of Huntington Beach. Have you been there? Surf City, groovy, wide beaches, great place. It's 9.5 miles wide or long. If you go out, water depth's an average of about 20 feet or so. Go out a mile, that's how much water they draw in every year. So that's a fairly good chunk of water. And they discharge half that again in brine, which is twice the salinity of seawater, and marine life can't live in that here, and so you've got to dilute that. So that just gives you a scale of what we're talking about here. Okay, I'm going to switch gears a little bit. As complex as all that was, those are the concerns of the state resource agencies, the state and regional water quality boards, the Coastal Commission, State Fish and Wildlife, the federal agencies, sometimes they have a role. These are the things we deal with. But here in California, most water supply planning happens at the local level. We have our big projects. We've got the tunnels, we've got Shasta, we've got the State Water Project. But for the most part, water districts, the thousands of them up and down the state, make their own decisions as to what projects they're going to rely on, how much water they expect to need over the next so many years, where they're going to get that, how much per capita use they're going to expect. And so the trick is to coordinate these two levels, all the state requirements and these local decisions. Just to illustrate that, this is Metropolitan Water District, the largest district in Southern California. It covers everything from near Ventura all the way down to San Diego. They have quite a few member agencies. These are actually the larger agencies. If you zoom in just on a part of Orange County, each of these is its own water district. they make their independent decisions about how much water they need and where they're going to get it and all that sort of thing. And so right now, Huntington Beach, the desal proposal there would be built here, but we don't know yet who here is going to say, yes, we're going to buy that water, or no, we don't need it. Or we've projected that we're going to need that in 15 years, but not until then. Or we've still got conservation we can do that's cheaper, so we're not going to participate in the project. So all those sorts of decisions get made at the local level. And they make a lot of decisions. They have to come up with the urban water management plans every 5 years, and we're going to get another batch very soon. They have to consider growth. How much are they going to allow? It's especially important within the coastal zone, which, depending on where you are in the state, can be just a few blocks wide in some areas to several miles inland. And in the coastal zone, you're not supposed to grow beyond the capacity of the coastal resources there. So you can't build more houses than you have highway for, or you can't build more residential or commercial development than you have sewer systems for, that sort of thing. And so they've got to consider that in their water planning. They also have to consider other options. Can we do more conservation? Is water recycling an option for us? Is it acceptable to our ratepayers and our citizens? How much are we willing to pay for a local supply versus a supply from far away? You know, all it would take is one good earthquake to knock out the state water project for weeks, months, not years, hopefully. Are you willing to pay more for desal just in case that happens? Those are all made at the local, those decisions are all made at the local level. Also, is desal replacing a supply, freeing it up for someone else? Or is it a new supply on top of everything you're already using for new development? And if so, who pays for that? The new development or the existing ratepayers? These are the battles that happen at water districts up and down the state on not just desal, but all sorts of water supply issues. They also often do an alternatives analysis, a more formal decision-making process. And this happens at the state level too, often through CEQA, the California Environmental Quality Act, where you look at all sorts of things. Is this a good location? Are there better locations where the environmental risks or harm would be less? Is it, you know, close to the existing plumbing or not? You know, what kind of intake options do we have? Is there an existing intake? Is there an existing discharge that we could use to lower our costs and reduce environmental impacts? So all those sorts of decisions have to be part of the process. You cite to consider entrainment. Generally, the closer the intake is to shore, the higher the entrainment. The plankton density is higher in shallow and near-shore waters. If you can move the intake further offshore, it'll cost a little bit more, but are you going to reduce the entrainment? Same with the discharge. If you are discharging into a kelp bed, that's not going to work. The brine is going to kill off the kelp bed. Certain species can't handle salt levels higher than the natural salt levels in the ocean. So you've got to determine whether those species are present near your discharge. If so, maybe relocate or put on diffusers, that sort of thing. On land, we've got issues. Is there sensitive habitat nearby? How close are you to the plumbing I mentioned? And this is something that is entirely at the local level. How much does it cost? Generally, right now, desal $2,000 an acre foot, plus or minus. The large-scale facility in Carlsbad is about $2,200 an acre foot, and that gets benefits of scale. It's a very large facility. Usually the smaller the facility, the higher the per unit cost. Right now, the most expensive water I know of is about $10,000 per acre foot for a small facility in Cambria that isn't even entirely seawater. It's a brackish system, but it's very small and they have a unique system, and they're paying 10 grand per acre foot. What are the rates here for ag water? I think 40, I think I heard this evening. So a big difference. Desal costs a lot of money. You also have to be concerned about the cost of distribution. One thing in California is our water system is built so that water comes from inland and high up to the coast, generally in that direction. Desal would reverse that. You're taking water from sea level, pumping it inland and upland. That's a big cost. The energy cost to pump water uphill is pretty steep. And depending on what kind of energy you're using, it can have pretty significant greenhouse gas implications as well. If you can use renewables, that's great. Australia has some very large desal facilities, about the size of the one here in Carlsbad. They have 4 or 5 of those up and down the state. They're run entirely by renewables. They went for this coordinated system, nationwide system to go for desal, but to have them be carbon neutral. The Carlsbad plant uses about 35 kilowatt hours. It generates about it uses 320,000 megawatt hours a year. That's about 90,000 tons of carbon a year that they have to make up for because they're using conventional systems. That's a cost too. They have to buy carbon credits or do some sort of offset for a lot of that. There's also the opportunity cost. If you're a local water district and you're going to spend all this money on a desal facility, does that mean less money for conservation, for paying people to put in low flow shower heads, or more efficient toilets, or tear out part of their lawn, or that sort of thing? Those are very low cost ways to save water. By putting all this money into desal, are you foregoing those opportunities? On the other side, how much is it worth to you to have a reliable local water source? The ocean's not going to dry up during a drought. If you're not worried about the water coming a great distance over the Tehachapies or through miles of aqueducts and earthquake faults and all that sort of thing, there's some benefit in having a desal plant right there, providing at least part of your local water supply. So if the worst happens, you're still covered for part of that. What's the premium you're willing to pay for that? That's a local decision. With all that, it's a fairly simple flow of the permits to go through. Start with CEQA. Actually, before you start with CEQA, you should do a lot of coordination, like meet with the agencies beforehand, figure out the design, the best location, all that sort of thing. The more of that you do, the easier the process is going to go. But go through CEQA review, get the local permits, get the landowner approval for the site. Along the coast, that usually means the State Lands Commission that manages all the state's tidelands. And so for any intakes, you'll have to have a lease to use the state's tidelands, whether it be a subsurface or an open water intake. Get your coastal development permit, get your approval from the Regional Water Quality Board, and start construction. It's not quite that simple. So the process I just described is this part of the process, the little crosshatch. The local process, all those decisions that get made before they even start permitting, How much water do we need? Where are we going to put this thing? Who's going to design it? You know, RFPs for the engineering, all that sort of thing. That happens here. You get your permits. Do you have the funding in place? Do you got to get grants? Do you have to get some sort of loan? If it's a private firm, they will, you know, issue bonds or do some sort of financing mechanism. That takes a while. And actually, the state that the permit process is a fairly small percentage of the overall time that it takes to get to a desal facility. Construction's not that long. The plant in Carlsbad took 2 years or so to construct, and it was a pretty sizable undertaking, a lot of concrete poured for that. But the main thing was all the decisions that went in before that, including who's going to buy the water. If we produce it, do we have enough customers? So, all that said, there are easier ways to do desal and more difficult ways. From the Coastal Commission perspective, if you're not right on the shoreline, that's a good thing. You're not blocking public access to the beach. You're not taking up valuable coastal property that could be used for visitor serving or other coastal dependent uses that really need to be right there on the water. So the closer you are to the shoreline, the more difficult your review is likely to be. If you've got a subsurface intake, it's probably going to be a lot simpler for you to go through the review. I didn't mention that if you are going with an open intake and you have to do one of these entrainment studies, the studies cost about $1 million and they take a little over a year to do. So you've got to build that into the timeline. Whether you're public or private can make a difference. Financing and also the kind of information you can share about your project might make it easier or more difficult to go through the process. If you're providing water for a particular area and everybody knows where that is and they've got an urban water management plan that says, yes, we need this water from this facility at this location, that's very simple compared with, we just want to produce water and see who will buy it. That's a harder thing to go through the process. That kind of leads to the next one. If it's part of a plan for a water supply versus this kind of let's build it and see who will come idea. And the more coordination you do with all the agencies, the easier it's going to be, hopefully. I hope we have a good role there. So the basic question, though, is what's the least environmentally damaging and feasible way to provide the needed water supply? A lot of places have gone down the desal path and they've got to this question and said, yep, got to do desal, that's the way we're going to do. Others have said, you know, we don't really need to do that. We've still got conservation we can do a lot cheaper. We've got a recycling opportunity. We don't need to do desal now. We may in 5, 10, 20 years, whatever, but for now, we have a different answer to that question. This is courtesy of one of the world experts on desal, Tom Pankratz, who does a global desal newsletter, travels all over the world, has seen pretty much every system in the world, as far as I know. Do you really need it? Have you addressed all the environmental issues? Does it make sense financially? Are you hiding the ball? Does everybody know what's really going on here? And don't take any shortcuts. So, what's the answer? Yes? No? Sure? Maybe? If you don't have the answer yet, a few good online things for you. The State Water Board just adopted last year a desal policy. It just got approved in January, so it's now in effect. It's online and all the background information that goes into great detail on all these issues. And basically it requires that desal use the best available site design technology and mitigation measures to minimize the intake and mortality of marine life. So that's the guiding regulation of the state right now. There's also a Coastal Commission report from a few years ago that goes into more depth on the Coastal Act issues. The state had a desal task force in the early 2000s that have, it's like a 2 or 3 page basic guidelines of how to do desal. And then if you have questions for me, I'm happy to take calls or respond to emails. And with that, I'll open it for questions.